Welcome to Aerodynamics. We continue the elementary potential flow solution for the potential flow theory. So the first elementary solution we have looked at is the uniform flow, and it satisfies both Laplacians for the velocity potential and for the stream function. And we moved on to describe the sink and source flow elementary solution. So the sink and source flow have a point source or a point sink to which or from which all streamlines originate or end. And we described the stream function and the velocity potential. So now we said that a solution, because of the linearity of the partial differential equation, the del square phi and del square psi equal to 0. These are the Laplacians. Because of their linearity, then if we have two solutions that we have found, then when we sum them, we get a third solution, and that would also be a solution to the Laplace equation. So when we add a uniform stream, so we said we could add the stream function, or we could add, so as you see here, we're adding the stream functions, stream function 1 plus stream function 2. So that's what we get psi 3. So we could add the stream functions, we could add the velocity potentials, or we could vectorially add the components of the velocity vector itself. So when you do this, you end up with this type of, you end up with a group of streamlines. And one important streamline is called the stagnation streamline, as you will see in a second. But to summarize the story, the stagnation streamline will form a closed or semi-closed shaped body, such as you would see over here. And because the definition, and you will have streamlines inside that closed body, as you see over here, and streamlines outside it. But since the streamline defines a line where there's no mass flow through it, it also describes a solid body. So we call this the semi-infinite Rankine. So let's look at how we analyze this type of system. An important point to find this streamline is to find the stagnation. The streamline that describes the body is to find the stagnation point, and the stagnation point will be on this particular streamline that has a closed form, that has a closed loop format, or it is shaped as a semi-infinite closed loop. So we have the we can get the tangential velocity for both for both streamlines from deriving the stream function, and we can get the radial velocity, as you can see here. And our goal now is to find the stagnation streamline. And to find the stagnation streamline is the streamline on which the stagnation point lies. And the stagnation point is the point where the velocity, the magnitude of the velocity, vr squared plus v theta squared is equal to 0. So that's what you have. So we can sum them up, but since they're not numeric, it's easier to find the thetas and r's where the v theta is 0, and to find the r's and thetas where the vr is equal to 0. And so let's look at the tangential velocity. So the tangential velocity is minus u infinity sine theta. When do you get sine theta equal to 0? You get sine theta equal to 0 at 0 and pi. So for all r's, because there is no r here, it's independent of r. So it's for all thetas equal to pi and 0. And then let's look at the VR. So VR is equal to 0. Let's see. How do you get a VR equal to 0? So when this term is equal to the minus of that term. So you get cosine theta equals to lambda over 2 pi r, and you get that for theta equal pi and for r equal to lambda over 2 pi u infinity. So these are our two. And where is the intersection? Where are the point between this v theta equals 0 and v r is equal to 0? So the intersections would be, so this is for all r, and this is only a specific r, so the intersection would be at this r. So what do I mean by intersection? I mean by intersection, when does v theta at the same time is equal to 0 as vr? So when vr is equal to lambda over 2 pi u infinity, and when r is lambda over 2 pi u infinity, and when theta equal pi. So the vr here gives us the is more restrictive than the v theta. So this is our stagnation point. It gives us the r and theta for our velocity v to be equal to 0. Very well. So that gives us and let's see where is this point. One is, we haven't talked about our coordinate system. So our coordinate system is, this would be r, and theta is measured counterclockwise from the x-axis, and we can go between Cartesian and radial and polar coordinate system, x, y, or r theta. So theta is measured from the positive x-axis in a counterclockwise, measured in a counterclockwise fashion. So this is the point where the velocity is 0. So it is at r equal to lambda over 2 pi u infinity. So this is 0. So this is r equal to 0. So we get r equal lambda over 2 pi u infinity. So it'll be on this radius. That's r equal to lambda over 2 pi u infinity. And at pi, so this would be the intersection of those two lines. So this would be our stagnation point right over here. So the stagnation point, on the stagnation point, there's the stagnation streamline. So we now, what we have found here is we found just a point where the velocity is 0. So let's see what streamline lies on that velocity equal to 0. So we have r, and we have r stagnation point and theta stagnation point. So let's plug r stagnation point here and theta stagnation point here, and let's see what we get. So you get, so instead for this r, implement lambda over 2 pi u infinity. So that's lambda over 2 pi u infinity. So the u infinity cancels out, and so on. And for the theta, plug in a pi. So for this theta, plug in a pi. So the stagnation streamline, so that should be sub s. The stagnation streamline, the value of it is lambda over 2. It's just a value of the streamline. This streamline could have a value of 1. This streamline could have a value of 2. This could be 8.5. This could be, you get the idea. So this guy right here, the one that we're particularly interested in, and actually it includes that, has a value of lambda over 2. And what is lambda? It is the strength of the source. So that's our source, and that's our uniform flow. So it comes from the source, and it has got to do with how much mass flow rate goes, or volumetric flow rate is being ejected from that source. So that's the strength of the source. So let's continue. We found the stagnation streamline, the value of it. Now let's find its shape. So we want to find what equation describes those red lines. We sort of started the solution ahead of time. I showed you the solution, but now I'm telling you how we got to it. So these are the steps. And now we want to find this shape. So what is this shape? We found the stagnation streamline, which is lambda over 2 is the stagnation streamline. So plug it here. So you're going to get so we'll put lambda over 2 would be equal to u infinity r stagnation. So now you're going to get a relationship between r stagnation, theta stagnation. And the relationship between r and theta is just a relationship between x and y. So that describes x equal x of y, or y is equal to y of x. Y of x, if you will. Y is equal to y of x, or x equal to x of y. You get the point. So that's the sigma, the stagnation streamline, and plug that here. So you're going to get a relationship between r and theta when you plug lambda over 2. So you're going to get r as a function of theta for the stagnation streamline. The shape now, what does the line look like of this streamline? It's going to have this 1 over sine theta relationship multiplied by a theta. And how does that look like? So if you take the sine theta, remember r cosine theta gives you r cosine theta gives you an x, and r sine theta gives you a y. So when you take this sine theta stagnation, in fact here, when you take r times sine theta, you're going to get a y. So now we're sort of mixing now two coordinate systems because it helps us plot it easier. So we're mixing the Cartesian coordinate system with the polar coordinate system, which is fair enough when we try to plot this over MATLAB or any type of plotting software. So we get a relationship between the height of the streamline above the x-axis and the angle theta. So for this theta, I would have a height of y given. So I get theta versus y. That's theta, and that's y. So it gives me this point. And when you, so let's try theta is equal to pi. So when theta is equal to pi, right here, so you're going to get 0. So the y is going to be 0 for all theta equal to pi. So right here, all this, so that's part of the streamline. And then when you move forward, when you move past this point, r is equal to what did we find it to be? We found r to be equal to, past the r equal lambda over 2 pi u infinity, we get this line over here. So that's a semi-infinite Rankine body. So then how did we plot this? We plotted it using MATLAB or Excel or whatever angle. And we now just checked these angles of theta equal pi, and let's check theta equals 0. So what happens when theta equals 0? When theta equals 0, you're going to get the maximum height to be lambda over 2 pi u infinity. So that is theta equals 0. So the height of this streamline at infinity. So when do you have theta equal to 0? It's when you go completely towards infinity in your system. So the height would be this height, lambda over 2 u infinity. Very good. So yeah, so that's what we have over here. So let's just erase the pen. So okay, so these are the dashed line is our streamline. Now, why are we doing this whole thing? we're doing this whole thing. What is the potential flow theory going to help us find? One, it's going to help us, is going to tell us what is the flow pattern around the body is going to be. So it's going to give us streamlines, but also importantly, it's going to give us what the velocity on the body is. Remember, slip is allowed. What the velocity on the body is going to be, and once we know what the velocity on the body is going to be, we're going to be able to find the pressure over the surface of the body, which is a basic contributor to the aerodynamic force generation, is the pressure. So we want now to find the pressure, and that is done through Bernoulli. So now that streamline, this closed streamline over here, we're going to call it B, the body, because here that's a semi-infinite Rankine body. So on the streamline, we have a velocity and we have the pressure at the body, and that streamline extends from infinity, so on the dashed line. So remember, Bernoulli is defined on a streamline, so we can take 2 points on that streamline, a point at infinity, so that's sufficiently upstream of the body, and a point on the body, so we can get what the body pressure distribution looks like. And the first point we are interested in is to find what is the stagnation point. This point, what is the pressure at this stagnation point? Which we can find it right over here. So the stagnation point has a V infinity is equal to 0, so you plug V infinity equal to 0, and then we can find the body pressure distribution over the whole surface, which is that over here. And we want to define a pressure coefficient, which we have actually seen before in the previous chapter. It is the pressure on the surface of the body minus P infinity over half rho V infinity square. So it's a non-dimensionalization of the pressure. So the pressure coefficient, so this is the one equation you would like to remember to find the pressure, is that the Cp is 1 minus V body over V infinity square. That's all you need to know. So what happens when you put the V body to be the stagnation velocity? What is V stagnation? V stagnation is 0. So your maximum Cp is going to be 1, because this term is always positive, and the maximum Cp is when this whole term is 0. So when V body is, so the stagnation point gives us the maximum pressure in our system, and from that point onwards, the pressure is actually going to be at any other point other than the stagnation point, the pressure is going to be equal to it or less than that. Typically it's going to be less than that, and it can go negative easily, so that's no issue. It can be maximum 1, but it can go negative. As we will see, it's going to be -3 for a cylinder. So we call this body a semi-infinite Rankine, and you will see that if you look at the shape of an airplane, the nose of an airplane, it sort of has a similar shape to our Rankine oval, semi-infinite Rankine oval, or Rankine body, if you will. And many other aerodynamic shapes have this same shape. So it does have practical applications, and it's not just a theoretical body, but it also is it has inspired different shapes of, it looks like a bullet too. And now we can see what the pressure distribution around it and so on, and what pressure loading is going to be on there. So now let's take this one step further. We added a uniform flow. We added to it a uniform flow, a source flow, and now what we want to do is let's add a sink flow right here. So what that will do is we'll actually bring the streamlines right over here. It will close this body. Instead of it being semi-infinite, it's actually going to be a finite body. So uniform, source, and sink together. But let's choose the source and sink to be of equal size, of equal strength, the gamma, and that's what you have. So you have a uniform flow coming here, you have a source, and you have a sink. So without the sink, our streamlines would go to infinity. And we were able to find what the height of the streamline at infinity in the previous slide. But if I put a sink now, what you'll have is that the streamlines will close much sooner. Will close at a designated point right here, and we're going to get that particular streamline to be completely closed body. So I'm not saying that there aren't streamlines inside. Yes, definitely there are streamlines going inside from the source to the sink and so on. But we don't really care about them. I'm interested in what the pressure around this surface is. So I'm trying to find a way to predict pressure and around the body. So now I've created a body, and now I can predict what the pressure is going to be. So the same story. We sum up the three solutions, either in velocity, either in stream function, or either in velocity potential phi. We sum them up. We find the velocity We find the velocity field, and then we find the particular points where the velocity field is exactly equal to 0. So these are called the stagnation points. Then we will find out that there is a stagnation point here, and a stagnation point at point B as well as point A. And we plug the values of r and theta, or x and y, of those stagnation points into the formula of the streamline. So we are going to get a streamline psi equals 0 is the line, the streamline that goes through points A and B. And in fact, A and B do this too. So A and B are the stagnation points, and we found the stagnation streamline. We didn't find its shape. We only found its value, its magnitude. Then our next step is to find its shape, and to find its shape, you want to plug in for the r and theta stagnation, or x stagnation, y stagnation, into the value of the stagnation function right here. So you plug r stagnation, theta stagnation, and now this system is a slightly bit more complex to do analytically. It's much easier to do through a plotting software, because you have two. Here it's given in terms of actually three coordinate systems. We have theta, r and theta, then we have theta 2 and theta 1. So theta 1 and theta 2 are relative to the source and sink, while r is measured actually from the center point between the source and the sink. So it's going to be much more complex to do this analytically. It's much easier if you do it with a plotting software, and we prefer MATLAB. So next we will go over the MATLAB plotting of these, of how to plot those over MATLAB and how to plot the streamlines. So as we said, then you have that. We found the stagnation point, we found the A and B, and we find the distance from point O, the origin, and A and B, and this is that distance, B square lambda over lambda B over pi V infinity. And then we find the value of the stagnation streamline, which is 0, and then we find the equation that describes this stagnation streamline, which is this. So you plug psi equals 0 right here, so that's equal to 0, which is from here, because that's the psi, and we get a relationship between r and theta, and that's a relationship between r and theta. In fact, we have theta 1 and theta 2. So that is very easy to plot over MATLAB. You might need 10 lines to define theta 1, theta 2, r, and theta, but then it would be very simple to define. So now we started now generating useful aerodynamic shapes, and if I'm interested in finding what the pressure at this point is on the Rankine oval. We call this the Rankine oval. It's not a semi-infinite, it's just a closed Rankine body. Or this point, I need to find what its r and theta is, and I can find the velocity v, and from that velocity, or v body, from that velocity v body, I can just go to the pressure coefficient and find what the value of the pressure coefficient, which is, once you find the pressure coefficient, the p body is straightforward. Once you know what your p infinity and v infinity are, which are always necessary to be given. So now we want to go into more familiar shapes. So we need for that to define a fourth elementary solution, which we call the doublet. And the way that you create a doublet is if you take a sink flow and put it on top. So let's take that sink flow and put it right on top of the source flow. So we're doing this. So now they're on top of each other, and you'll see when you put them on top of each other, the velocity will identically cancel out for all r larger than 0, right? The radial velocity will identically cancel out. But when you put in r equal to 0, when you sum up the source and a sink, you're summing infinity minus infinity, and infinity minus infinity does not actually equal to 0. It's not equal to, it doesn't necessarily have to be equal to 0. It can, but not necessarily. So we need to use something like limits. We need to find the limit when r is equal to 0. What do the streamlines look like? Because we found that when outside r equal to 0, sure, the source, the radial velocities will identically cancel out. So let's do this. And there's an elaborate mathematical technique in the book that we are just going to go over really quick. So let's now put a source and a sink. So that's a source and a sink right next to each other, but now they're separated by a distance L. So that's why they're not. So I put a source and a sink, and each one measures an angle theta 1 and theta 2. That's why I have theta 1 and theta 2. So let's so here's what we have. We have a source and we have a sink, and they're separated by a distance L, and the difference in angle theta 1 minus theta 2 is the delta theta right over here. So you can pick a control point somewhere and find what the contribution of each one of the source on that point and the sink on that particular point. So in the definition of the doublet, the source and sink are of equal strength, and what we want to do is to make, if I want to put the source on top of the sink, this L is going to go to 0. But I'm going to define, to make my definition of the doublet, is that the L times the strength remains a constant as I make L go to 0. So that's the definition of a doublet. So we're going to define this L times lambda to be the kappa, which is the strength of the doublet. The gamma is the strength, the lambda is the strength of the source or the sink, while the kappa is the strength of the combined source and strength when they're separated by a distance L of equal to 0 or close to 0. So let's take the limit when L goes to 0. So delta theta becomes d theta from this equation right here. So that's our stream function, and we can go through this elaborate. So there's quite a bit of geometry here and derivations, but what we want to do, what we are after is, you can go over. So here, when you go through the limit of L equal to 0, you see where it helped us to to define the kappa, L times lambda, so that becomes a constant. So you get a constant here, and plug L equal to 0, then it's no issue. So that cancels out, L equal to 0. So you're going to get kappa sine theta over 2 pi r, which is fine. So that's the definition of the streamline for a doublet, and from that follows the definition of a velocity potential. From those you can derive the velocity, the Vr and V theta, or Vx and Vy. So that's our doublet flow. So let's look. This is the stream function, and this is the velocity potential for a doublet. And you look, let's set r equal, let's try to plot one of those lines. Let's set r equal to constant. Actually, yeah. In fact, no, we want to set psi, forget about that, let's just erase that pointer. Erase pen. Let's set, we want to see what a constant, what does a constant streamline look like? So what is the shape of these streamlines? So set psi equal to constant. So you're going to get r of a streamline, not stagnation, streamline is equal to sine theta, some constant times sine theta. So r is equal to sine theta. Sine 0 is 0, and as you go to sine 90, you're going to get a maximum, and then sine, so that's sine pi over 4, sine pi over 2, sine 3 pi over 2, and then sine pi. So you're actually going to get a circle, the shape of a circle. And that's what the streamlines look like. And if you get, so what you'll see is if you change that constant we just talked about, that c right over here, you're going to get to a different streamline, and so on. And what the sine actually, and then you can actually compute the velocity, and the velocity will give you Vr and V theta, and you just check the V theta, and if so, you'll see when you have a minus sign, your V theta is going to be what that minus sign tells you is that this V theta is for positive kappa, your V theta is going to be positive, so you're going to get a clockwise, and when kappa is negative, you're going to get a counterclockwise rotating doublet. And this thing is symmetric top and bottom. And now you can try and plot the stream, the velocity potential. So velocity potential is constant, so you're going to get, so that is equal to c, a constant. So you're going to get r is equal to kappa cosine theta. So the cosine thetas are perpendicular to sine thetas, so you're going to get those cotangent circles of reducing radii, so they're perpendicular to each other. So if you look at those two lines, they'll be perpendicular. Stream functions and velocity potential lines are perpendicular to each other. So that's the doublet, and we need it because we are interested in the case when we take a uniform flow and add it to a doublet flow. What we're going to get is actually the flow past the cylinder. So you get a uniform flow, you get a doublet, and you're going to get the flow. You're going to get a complex set of streamlines in the, but let's ignore what happens on the inside. And we follow the same steps we had before. We find when the velocity is equal to 0, it will be 0 at A and B, which we call the stagnation points. And we find the streamline that passes through those stagnation points. So it will be this streamline, and it would be a circle centered at R circle centered at the origin here at r equals 0. And that's the flow around the cylinder, and the cylinder is actually a very important canonical fluid mechanic or aerodynamic shape. You see it in a number of engineering applications like risers in the sea and wire lines, electricity wire lines, and so on. So it is a canonical shape that we are particularly interested in looking at. So now we know what the drill is. We find the stagnation streamline, and then we find its shape. So we set psi equal. So we found here that the value of the stagnation streamline that goes through the stagnation point is 0. So now you set pi to psi is equal to 0. So you end up with a relationship between r and theta and so on. So you'll get a relationship between r and theta. So here actually we're deriving the whole thing. So stream function, and then so that's your stream function, and let's just put this whole thing kappa over 2 pi v infinity, kappa over 2 pi v infinity. Let's call it r square right there. So here we're summing the two streamlines, and then we find, let's just to save space, we'll call it capital R, and then we find the v theta and vr, and we find when they are equal to 0. So when is vr equal to 0? It's equal to 0 when capital or small r is equal to capital R, so it's 0, or when theta is equal to 90 degrees or minus 90 degrees. So that's when VR, so VR is 0 along this line, as you can see, which makes sense. You can actually just look at the plot. Where is the radial velocity 0? I don't have a radial velocity component at 90 degrees or minus 90 degrees. And my VR is equal to 0 also for all thetas and for this r, but that's only VR. We need also to see when is v theta is 0. V theta is 0 only when sine theta, so 1 plus r squared. So v theta becomes 0 when sine theta is equal to 0. So that's equal at 0 and pi. So we have those lines, right? The circle and the perpendicular line are the zero value of VR, but the theta equals 0 and pi, so this line over here, all this line, theta equals 0 and theta equal pi, that is when v theta equal to 0. So actually I should just plot it, so let me just erase it and use a different erase. Let me erase this guy, and use a different color pen. Okay, so let's use a blue. So that was the red was VR, and for v theta is 0 when sine theta is 0 and pi. So we get those two lines. That's theta equal pi, theta equals 0. And when is VR is 0 at the same time as v theta? It's at the intersection points here and here. So these are our stagnation points, A and B. And A and B are located at small r equal to capital R. So our stagnation point is at r equal to capital R, and theta equals 0. So we have 2 points, theta equals 0. That's point number 1, which is this point right here. And the second point, stagnation point, is r equal to capital R and theta equal to pi. theta equal to pi. So this give us the two stagnation points, and the stagnation line runs through them. So I have a stagnation point at upstream of the cylinder and downstream of the cylinder. So we found those stagnation points right here, and we get the stagnation stream. So actually we found the stagnation, then we find the stagnation streamline, which is psi equal to 0, and then we plot the stagnation streamline. So we set it equal to 0 right here, and we find an r as a function of theta, and we'll get those the two red lines. That is my stagnation streamlines. Okay, so what we're after in the end, so we have on the surface we have Vr and V theta, but on the circle we only have tangential flow. There's no here you only have tangential flow, because on the circle Vr is equal to 0. So it's easy. So now I plug for the V, which is Vr square plus V theta square, but since Vr is 0, I'm just going to plug for the V body to be V theta. So plug V theta for V body here, that's V body in the pressure coefficient. So now we find the pressure distribution over this whole surface, over the cylinder surface. And what you'll notice is that the pressure distribution is 1 minus 4 sine square theta. Sine theta can go from +1 to -1. So when it's sine theta is so when 4 sine square theta is equal to or actually when sine theta is equal to 0, I'm going to get the stagnation point. So that's the maximum pressure I'm going to get. So my pressure is maximal at the stagnation point, and as I move further away from the stagnation point along the body, stagnation point means my velocity is 0, maximum pressure, and as I move away from the stagnation point on the body, my velocity increases and my pressure decreases, and I get a maximum or a minimum pressure when sine theta is equal to 1. So 1 minus 4, I get a Cp of -3 at theta equals 0 and pi over 2. So Cp is -3. And then so pressure here, I have a favorable pressure gradient because I have the highest pressure, lowest pressure, Cp -3, Cp0 at the stagnation point, Cp1, I'm sorry, at the stagnation point, and Cp -3. But then, so in this region, I have a favorable pressure gradient, and in this region, I start with a minimum pressure, and then the pressure starts increasing until I get to Cp is equal to 1 again. So here I have an adverse pressure gradient, and let's look at that. If I draw the very far away streamline from the center line, so that's very far away, so that's also considered infinity. I don't get the effect of the cylinder. It doesn't deflect that streamline very, very far away. And look at the distance here between the two streamlines, the stagnation streamline and the infinity streamline. You'll see the distance is actually decreasing, and the distance between, because I'm looking at, let me show you what or just explain use better color. Yeah, let's do it actually. So I now have streamline A, and I have streamline B, and what you get, if you look at the distance between the two streamlines, I get a constant mass flow rate between those two streamlines, because mass flow rate does not cross a streamline. So that's my streamline. And you'll see as I get closer to the body, here's a stagnation point. As I look at the distance over here, my mass flow rate is going through a smaller area, so it has to speed up, and I get the minimum area right here, so I get the maximum velocity. But then as I move further downstream, the area starts opening up again until I get to my stagnation point again, and then my flow tends to become more and more uniform further away. So you'll see I get a region of a favorable pressure gradient. The pressure gradient is trying to push the flow to help me because the pressure is high here, it's low, so it's helping out, while the pressure is low here and pressure is high here, so it's actually trying to retard the flow. Remember this favorable and adverse pressure gradients. We're not talking about pressure, but pressure gradients, difference in pressure with distance, because it's going to come handy when we discuss the actual flow around a cylinder. So here's what the cylinder, you plot Cp1 minus 4 sine square theta as we just described before. So at the Cp1, so here's my Cp and here is theta. So Cp1 is at the stagnation points, so at the front and the back. So this is the front, and this is that point, theta equal pi and minus pi, they're the same point. So this is the bottom travel path and this is the top travel path, and you'll see they're symmetric. So the cylinder is symmetric up down, but it's also symmetric top down. That's the top down, that's the bottom to the left, top to the right. So it's symmetric top down, so that's the top bottom, but it's also symmetric around theta equal to 90. So it's symmetric around pi over 2. So you'll see this region here. It's symmetric top down and left right. So this becomes important when we're looking at the forces. So if my flow is symmetric left right, then the pressure on the left and the pressure on the right, the pressure distribution on the left and on the right are equal, so they're going to cancel each other. I don't get any drag force. And if the pressure on the bottom and the pressure on the top are the same, I'm getting equal pressure, so I don't get lift. So I don't get a force perpendicular to the velocity v infinity, and I don't get a force parallel to v infinity, so I get no drag. The last elementary solution we are going to look at for the potential flow as a potential flow is the vortex flow. And the vortex flow, as you can imagine, is just a rotational type of flow, as the word suggests, and it would satisfy the two Laplacian equations, the curl-free and the divergence-free velocity fields. So here's the vortex flow, and you'll see it's purely tangential in velocity. The streamlines are all concentric circles, and the velocity, the radial velocity, is 0, and it's only purely tangential. So you see that the tangential velocity has a very similar shape. Actually, it has the same shape to the radial velocity in a source or a sink. So you want to the stream functions and the velocity potentials between a vortex flow and a source sink are identical, and vice versa. So you'll see. So this is the last elementary solution we're looking at. So it's purely tangential velocity, and we're going to define this C, as gamma over 2 pi, so that would be, or actually minus gamma over 2 pi, that would be our circulation that we have seen before. So minus gamma over 2 pi, which the circulation would be our vortex strength. So the stronger the vortex, the stronger the gamma, which means it's going to rotate faster. That's what we're saying. And the vortex flow, just like the sink and source flow, satisfies the Laplacian equations on the stream function and velocity for the potential, which means it's divergence free and curl free, except when r is equal to 0. There is actually net circulation at r equal to 0. We get, but that's a singular point over here. It's a singularity. So we have the stream function, or we have the tangential velocity. We can now get the stream function, and so we have the VR is 0, and we have the v theta is given. So v theta is minus d psi dr. So we get the psi to be gamma over 2 pi log r. So that's our stream function, and we can get the velocity potential in a very similar fashion. And for the velocity potential, v theta is 1 over r d phi d theta. So we get phi to be equal, it's straight lines. So just like a source and a sink. If you plot that, these are my stream lines, and my velocity potential lines look like this, the radial lines. So it looks exactly the same as, or sort of the opposite of, or crisscross of a source sink flow, but it has a, in terms of math, but in terms of the shape of the flow, it looks completely different. This is purely rotational, and that's purely radial. Okay, so that is actually the last solution the last elementary solution we are going to need in here. And here's a summary of what we have done so far. We looked at the uniform flow, source, sink flow, so depending on the sign of this guy, and a doublet flow, and lastly we looked at the vortex flow. And depending on the sign of the gamma, your sense of rotation could be clockwise or could be counterclockwise. So you can play with that using the sign of the gamma. And these are the summary table of the velocity field, the velocity potential, and the stream function for all these elementary solutions that we had. And you can see you can derive one from the other. So these are all descriptions of the same thing. So you want to be familiar with all of them on how to get from one to the other and from the other to the one. So let's look at, now let's sum up the uniform flow and a doublet that gives us the flow around the cylinder, and then let's add some rotation to it. So let's add a vortex on top of that cylinder. So when I add a vortex, my cylinder is going to start to rotate. So that's what you're going to get, and it's going to mess up my streamlines. So it will make the streamlines on top go faster, and the streamlines on the bottom, because that is opposite to that over here, so it's going to subtract, while this guy is going to add up to this guy, so it's going to move faster on top and slow down on the bottom. And the flow now becomes non-symmetric. It's still symmetric left-right, so along the y-axis it's still symmetric. So you look at the shape on the left and the shape on the right. It's symmetric, which means that that the pressure distribution on the left is along, about the y-axis mirrors the pressure distribution on the right, which means I don't have a drag force. But now if you look around the x-axis, the center of the cylinder, that goes through the center of the cylinder, then my flow is non-symmetric top bottom, and you'll see the flow is actually slower at the bottom. You see you have stagnation points here than it is on the top, which means I expect higher pressure at the bottom than at the top, so, and lower pressure at the top, which means that is going to generate lift for me. So you see, with those 4 or 5 elementary solutions that we have started looking at, we were able to to do closed form shapes like the Rankine object and the semi-infinite Rankine, and then we moved on to do a circular cylinder, but all of them were symmetric, and they did not produce any lift, they did not produce any drag. And now with the introduction of the vortex flow, I am now able to generate lift. So you see the circulation is now an important quantity that will allow us to introduce lift into our potential flow theory. So we have now generated those a set of two, that summary table that we had here is our toolbox, and we can now mix and match between those items, and we can get different types of flows and bodies and shapes that that are of interest to us aerodynamically, and we can find pressure distributions around the cylinder. And now, with the introduction of the vortex, we are able to generate lift, which is great because that's what we're after. So if I take a cylinder and start spinning it, I expect that it's going to generate lift. So that system generates lift. And we could just tell that without doing much computation, just by looking at the shape of the streamlines. So when I sum those two solutions together, I end up with a rotating cylinder, and that's the stream function for that rotating cylinder. You get the vortex plus the cylinder flow. And the cylinder flow was the elementary solution of a uniform flow with a doublet. So we keep adding things up, and then we just use them as new elementary solutions. So let's see now what happens when I start playing with how fast I rotate my cylinder. So we're playing with this gamma, and you'll see as I start rotating my cylinder faster and faster. So when I have no circulation, when I have no circulation, that is, I don't have a vortex, my stagnation points are symmetric, so I don't get lift. But let's start playing with the circulation. So when the circulation is larger than 4 pi over v infinity r, which comes from the previous equation, and you can follow the derivation. It comes actually from here. So these are the stagnation points at which thetas. So we get 2 stagnation points for the k on the body when gamma is less than 4 pi v infinity r. As I start increasing my gamma, so when gamma is less, now I increase my gamma so it becomes equal to the multiplier of the velocity and the v infinity and the radius of the cylinder. I get the 2 stagnation points now start moving down, and they meet at theta equal to pi over 2, minus pi over 2. So I get 1 stagnation point. And now, as I increase my spinning faster and faster, so my gamma is larger than 4 pi v infinity, gamma is the strength of the vortex, so it spins faster and faster, the stagnation point leaves the body and now goes into the flow, which means you have a higher lift generation. So that's what the potential flow theory predicts will happen in a rotating cylinder. And we are now interested. We're excited about finding what the lift is going to be. And here you can find what the radial location of the stagnation point is going to be. So now we're interested in the pressure. So to find the pressure distribution around the cylinder, this is my cylinder, and the same cylinder, in either case, in one of those 3 cases, or any intermediary case, I'm after the pressure distribution around that particular cylinder. And when I find the pressure distribution, I integrate the pressure so I get the component of the pressure that acts in the y direction, so that's why you get this cosine eta thing. You integrate it over the surface of the body, and that gives you the lift. Now there's a theory, which is the Kutter-Tsiolkovsky theory, which tells you that the lift is actually, when you do this integral, you can try and do it. But you will find that the result of the lift is going to be the density multiplied by the V infinity multiplied by the circulation. So it's a second, it's the right hand rule. So you have V infinity in this direction, you have the circulation in this direction, and then you use your right hand that tells you that the lift is going to be out of the page, coming towards you. So these are in the V infinity is going to the left, to the right, sorry. The circulation is clockwise, counterclockwise, which means that the lift is going to come out of the page, out of the plane of the page that we are looking at. So this is the right hand rule that you can so now you can take your right hand, and you have your fingers pointing in this direction, and your thumb, and you rotate your hand, so you'll see that your thumb actually is coming out of the page towards you. Anyways, it's hard to explain here. So this is still potential flow theory, which means we don't have any boundary layer, and we don't have slip is allowed. As you can see, our cylinder rotates, and we can even in the non-circulation case, our cylinder rotates. And next time we will start talking about what happens when in real life. We will see what are the differences between what our theory predicts and what happens in reality in real life. Thank you.